I stopped the last lecture by celebrating the great success of the Higgs, but also pointing out the weaknesses. And the lecture of today will be devoted to understand what these problems are and how we want to go ahead with them. So, as I said, one of the, maybe you want to close the door? One of the important feature of the Higgs discovery is that we have seen a new force. We've really seen a fifth force, and now, obviously, we want to understand the nature of this force. Is this a weak force or a strong force? Is this new sector weakly interacting or strongly interacting? Is it a gauge force or not? After all forces that we know in nature so far were of a gauge nature. This new force, the one responsible for the electroweak symmetry breaking, seems a non-gauge force. Is that really true, or is there some hidden gauge structure underneath? Is this particle that we've seen, is it a fundamental particle, or is it a composite particle? After all, this would be the first real fundamental scalar in nature. So this is another question certainly to be addressed. And if you remember, in the first lecture, I have constructed the electroweak breaking sector in a completely independent way. I've just identified the fundamental degrees of freedom, which are the Goldstone bosons, and then constructed an effective theory of those bosons. And then there was no reference to the underlying theory. This could be some strongly interacting sector, weakly interacting sector, the Higgs model, whatever. But the important thing is that the identification of the effective theory was unique. Then, given that we've discovered a new particle, I coupled a scalar singlet to this sector in a most generic way. And then we've seen that the usual completion of the Higgs model gives up particular values for the couplings of this scalar particle with the rest of the sector. Well, that construction obviously is particularly useful when you want to compare and when you want to interpret the experimental data, because after all, we don't want to use the data just to check it with a special model, Higgs model, but we want to understand out of data what is the electroweak breaking sector. So if you take that parameterization that I was constructing, is the most suitable for the experiment, as I was saying. This does not work. The pointer is dead. But no, this is has to be switched up. Sorry. Thank you. So in general, you take a scalar particle which has a mass, and then you couple it. Since the coupling of this scalar particle is with the Goldstone bosons, will couple proportionally to mass to the W and the Z. Here, I'm putting the same coefficient for the coupling of the W and the Z, and this is a consequence of this custodial symmetry that we saw that was a necessary ingredient of the electroweak breaking sector. Of course, in principle, you could generalize it, but that seems a fairly reasonable parameterization given what we know about this sector. Then, in general, we'll have couplings to the fermions of the theory, which are proportional to mass. Now, we know very little about the structure of fermions, so in principle, all these couplings could be general. A reasonable starting point is to use one single coefficient for all the fermions, and then compare it to experiment. Of course, you can do better. You can do more complicated things. And then you can add higher dimensional operators, so couplings to of the Higgs of this scalar particle with FF dual kind of operators with a W, with a Z, mix the Z and photon, coupling of the photon and coupling to the gluon. So this is a general parameterization. Then you compare it to experiment and you do fit. And there's been an industry recently in this kind of activity trying to fit the data with general parameterization of this kind. And if you want to write paper, this is maybe a rewarding, a lucrative activity, because generally each paper gets 100 citations simply because there are 100 papers doing those kind of analysis. Sort of a logic of a chain ladder. But definitely it's an important activity because we want to understand. I will not present the result of all this kind of fitting because I think, important as it is, but it's a little premature in the sense that right now all these fits are driven by this discrepancy in Higgs into two photons. So we have to see what's going to be the final fate to that discrepancy before understanding. But let me just show you one kind of this plot done in this case by the CMS collaboration, in which you use two parameters. One is an overall scaling of the coupling to the gauge boson, and one an overall scaling to the coupling to the fermions. So it's this A parameter and the C parameter in that formula. And so you see, well, two things. One is that the various channels start already giving constraints on this parameter of the level of, say, 30% or so, which is a remarkable result. Also, you see that the standard model point is at the 1, value, okay? Because these new couplings are rescaled with the standard model value. So here is a standard model, and you see that the only one that somehow is off is a result of H gamma gamma. And in order to increase the rate of H gamma gamma, what you can do is you can, for instance, reduce somehow the coupling of the Higgs to fermions. Remember, the Higgs into gamma gamma has two kinds of contribution. One was a W loop, and one was a top loop. And those have opposite sign. The W loop dominates. So if you reduce the coupling of the Higgs to fermions, you reduce this negative interference between the two, and so effectively you are increasing H into gamma gamma. Of course, the reduction of the fermions you pay a price because you're also reducing the coupling of gluons to Higgs, which was a production mechanism. But you can compensate it by, for instance, increasing a little bit the couplings to gauge bosons, and so you increase the associated channel. So you see that this H to gamma gamma will try to push more in that direction. But as I said, we'll have to wait. Certainly, however, these kind of plots will dominate the future of Higgs physics, because there's a lot to learn from the couplings. Because inside these couplings of the Higgs bosons, they hide the real nature of this particle and of the electroweak breaking sector. So right now, it's really becoming an experimental question, the definition of what is this fifth force and what is this new sector. When we examine the standard model, however, we can note that almost all of its open problems really originate from the Higgs interactions. For instance, the coupling of the Higgs to fermions is the coupling that gives the masses to the fermions. But that is really a big puzzle. We're still far from understanding mass. We don't understand what is the structure. As you know, if I turned off the Yukawa coupling, the standard model would have a large global symmetry, because the fermions will be essentially like free particles coupled onto the gauge interactions, and therefore I would have a U3 to the fifth global group, which is called flavor group. In order to give mass to the fermions, it's not sufficient to break the electroweak symmetry, but you also have to break this global group. Now the question, so the emerging pattern of the fermions will be determined by the way you break this global symmetry. And maybe we'll see tomorrow if I have time, the way of breaking this global symmetry is very delicate, because now we have enough information that tell us that there are only very special ways in which you can do it. Others are excluded by experiments. And in the case of the case of the Higgs breaks this global symmetry by the Yukawa coupling. And it turns out, again, that is a perfectly successful way of doing it, because it complies with all the requirements on the symmetry breaking. However, it's just put it by hand. So all these Yukawa couplings are free parameters, meaning that you have no possibility of predicting the quark and lepton masses and mixing angles. Actually, they contain even more free parameters than observables, these Yukawa couplings. The second problem comes from the quartic coupling of the Higgs. And this is connected to the stability of the potential, and I will discuss it next. Then we have the bilinear term in the potential, the one that generates the triggers the electroweak symmetry breaking. And this gives rise to the notorious hierarchy problem, and I will talk also about it. And then, if you wish, you could also put the cosmological constant problem in the same equation, because after all, that's a constant, and you can call it a constant in the scalar potential. So really, all the big problems that we have in the Standard Model are all connected to the Higgs. And if you wish, they are really connected to the fact that this fifth force, this new force, is not a gauge interaction. In a sense, we've been spoiled by the beauty and the power of gauge interactions. And as I was discussing, they give this property of uniqueness, of robustness against deformation, and therefore predictivity in the theory. As soon as you go away from the gauge principle, like you do in the Higgs, you lose all the properties. And so, in particular, you have lack of predictivity, possibility of deformation, because you can modify the theory in many ways, and all these connected problems. So again, all these problems, if you wish, go back to the underlying question of what is this fifth force? Is this a gauge force or not? So let me start with the first problem, the one of the stability of the potential. So the Higgs potential can be written in this form, right? There's a quartic coupling and then a bilinear, which is related to the Higgs valve. So let me parameterize this in this way. If I'm interested in large field configurations, it's a very good approximation just to drop this constant. Okay, I'm interested in large fields, so that the fact of the weak scale is subdominant. Now, of course, when I go to large field, I have to be careful, because this is a three-level potential, and I get the large quantum corrections, which in particular have logarithm, which can be very large if I go to values of the field which are large. Now, there's a very simple trick with which you can take into account all these logs. Because if you see, this potential here is a potential that's only one scale, the Higgs field. There's no other scale. This one is irrelevant, okay? So that means that if I look at logarithmic quantum corrections, they have to be, in their argument, their renormalization scale. But the argument of the logarithm has to be dimensionless. And since I don't have any other scale in the problem, this log will be log of mu, the renormalization scale, divided by the value of the field. So that means that I can catch all the dependence on the field just by looking at the usual renormalization group equation and computing the dependence on the renormalization scale. That will keep track also of the dependence on the field. So this is a very useful trick, because then I know how to do calculation in a very simple way. So effectively, what I'm doing is I'm replacing this coupling lambda, when I go from the classical theory to the quantum theory, I replaced this quartic coupling lambda with a field-dependent coupling. And the field dependence is described by the usual renormalization group equation, which in particular, if I computed a one-loop renormalization group equation for the quartic coupling, has this form, these two lines. This second line is less important numerically because it includes gauge coupling. Of course, when you do precise calculation, you have to take it into account. But let's just look at the trend. So let's focus only on the first line of this equation, which tells you how lambda varies with the renormalization scale in terms of the quartic lambda and the Yukawa of the top. You'll remember that the quartic coupling is related to the mass of the Higgs. Okay, because the mass of the Higgs, when you minimize the potential, take the second derivative, the mass of the Higgs is lambda times the mass square lambda times v squared. So this coefficient here, which is very large, as you see, and is positive, is proportional, if you wish, to the Higgs mass. So the larger the Higgs mass you're considering, the larger the quartic coupling, the more the quartic is driven to large values as you move from low to large field values, or renormalization group. On the other hand, the Yukawa of the top has an opposite sign in the RG equation, so tend to push the quartic low as you move up in scale. So this is essentially the fact when I do a numerical calculation of the quartic coupling of the Higgs potential as a function of the renormalization scale. See, I go from the weak scale all the way up to some Guth scale or Planck scale or whatever. And you see that if I choose a low energy, so this is, if you wish, fixes the value of the physical Higgs mass. If I go up with the value of the Higgs mass, what happens is that this coupling tends to blow up, goes higher and higher. On the other hand, if I start with a lower value of the Higgs mass, lower value of the quartic lambda, the top effect becomes dominant, and this coupling becomes smaller and smaller. Actually, it can become even negative, because remember that renormalization is an additive renormalization. It's not a multiplicative renormalization. Therefore, this coupling can become negative. What happens when the coupling becomes negative? Well, the whole potential, which is lambda phi to the 4, becomes negative. Of course, you know, when I look at large field value, it's a h to the 4, which dominates the size of the potential. And the dependence on the field of the quartic coupling is just logarithmic. However, if I change sign, that becomes crucial, because all of a sudden my Higgs potential, which has the usual vacuum, electroweak vacuum, it grows like a fourth power, but then all of a sudden, since the coupling becomes negative, boom, it just suddenly goes negative. So that means that you're developing new kind of configuration that could minimize the energy. So the vacuum of your theory is no longer the electroweak state, the one that gives rise to the correct value of the W mass and all the other masses, but it could be in a very large field configuration. If I then look at, of course, this extrapolation that I'm doing in a large field, it depends on the scale up to which I trust my theory. Because remember, I'm just taking the standard model. So this extrapolation at large scale depends on my assumption that there is only the standard model. So you can question this assumption. One way of saying is that parameterize this as a function of the scale, the maximum scale up to which I can extrapolate my standard model. So you do this, and if I look at the evolution of the quartic coupling as a function of the scale, I'm finding that for large values of the Higgs mass, at a certain point, I hit a non-perturbative value. If I go to low values of the Higgs mass, at a certain point, I start developing another vacuum, and potentially I get an instability. Of course, then it depends on the tunneling probability, if we can live still in the electroweak vacuum or not. The tunneling probability can be computed with the usual quantum mechanical method, and it's interesting. What's useful is that the bound that you get is independent of the cosmological history, because the tunneling rate is always dominated by late times. So it doesn't matter what happens in the universe. It really when you compute the bounds, is what matters is only the late times. And you see that if you want to allow the extrapolation all the way to a very large scale, you identify a narrow window of Higgs masses up to in which you could live. So now we know what the Higgs mass is, and the Higgs mass actually happens to be very close to this boundary. Let's study the problem a little bit more in detail. So let me look, now that we know the Higgs mass, let's look at the evolution of the Higgs-quartic coupling as a function of the scale. This is the evolution. You see that what we find is that it becomes negative at a scale of the order of 10 to the 10 GeV or so. Now, there is a large uncertainty on this scale, which depends on the precise value of the top mass, the Higgs mass, and alpha s to a lesser degree of importance. Also, the situation is particularly critical because the running of this coupling, as you see, is fairly flat in the high energy domain. It means that this coupling, not only it becomes close to zero, but even its beta function, so the derivative of this coupling, is near zero. And this is just an accident. It doesn't look, there's not any good reason. You see that you started with a beta function here that contained very large couplings. This is the quartics, the Yukawa at the top. These are large numbers. And even the gauge at large scale are large numbers. And they just happen to nearly cancel. And there's no symmetry reason or anything like that. It just appears like an accident, maybe. So now I can look in a phase diagram of Higgs mass and top mass, which are the two critical parameters that, the two essential parameters that define the phase space of the Standard Model. And sure enough, I will find that there is a large area in which my theory is stable, and this corresponds to low Higgs mass. A large area in which the theory is unstable. This is for large top mass. And then there's also the possibility of non-perturbativity. Well, if I now use the experimental information and want to see where we lie in this Standard Model phase diagram, the answer is here. Actually, let me blow up this region for a minute, and the experimental information is here. And this is a fact. This is just a measurement. And just a remarkable coincidence, however, that we happen to live just at the boundary between the two phases, the ordinary Higgs phase and the region where the Higgs field instead slides to very large field values. As you see, the present data at the moment favor the metastable phase, in which our vacuum is not the lowest configuration possible, but the lifetime is longer than the age of the universe. That's what we call it metastable. But of course, we are really so close to the boundary that we will need the more precise experimental information on both the Higgs and the top mass in order to ascertain the ultimate fate of the universe, because this is not something that we should worry, because of course lifetimes are extremely long, the cosmological lifetime, but at the end this will be how our universe would end if we are on a metastable region. This graph is extrapolating up to the Planck scale, the standard model. So there's a strong assumption underneath. By the way, it doesn't really matter if you extrapolate to the Planck scale or somehow below, because the quartic I've showed you has a minimum and then goes up. But still, what's very important, however, is that you extrapolate it to a large scale. If the LHC discovers new physics, all this story completely collapses. Actually, this very soon we will know the Higgs mass very precisely, and so that the uncertainty of where we live will be dominated by the top mass measurement. And you see that the top mass measurement in the limit of stability plays a very important role, because every GeV of error that you put in the top mass counts as 2 GeV in the Higgs mass. So reducing the error on M top may really be sort of a telescope that will peek into the future of our universe to see if it's stable or not. Now, if it's really true that we live in a metastable vacuum, you understand that you could use this information to learn something about cosmology. Because just the fact that we are in a metastable vacuum means that the cosmological history must have been such that this configuration was never destabilized. So you can start thinking, oh, maybe, how about thermal fluctuation in the thermal universe? Can I learn something about it? Or can I learn something about quantum fluctuation during inflations, which were very large? Well, actually, we are so close to the stability region that there's not a lot that we could learn. If the Higgs mass had turned out to be few GeV different, the game would have been completely different. So we are really in a very special region. Because if I just look at what is the thermal metastability, it means the possibility that our vacuum was destabilized during the cosmological history by thermal fluctuations, even if I consider temperature as large as the Planck scale, thermal metastability requires that the Higgs mass is larger than 122 GeV. The Higgs is 125. So it seems that there's no problem. Of course, again, the errors is what counts, and there are large errors. So if we are 2 sigma off, then these arguments could play a role, and then we will learn something about, for instance, the maximum temperature in the universe. So that's a story. This is just an experimental fact. If I look at the gauge couplings and the top Yukawa coupling, and I renormalize them up to some large scale, I get this generic feature. By the way, if I had asked you which one between the 3 gauge couplings and the top coupling is the smallest when I go to large scales, you could ask this question to many theoretical physicists, and very few will tell you it's a top quark, top Yukawa. Top Yukawa is smaller even than G1 at that scale. But anyway, they're all typically of order 1. On the other hand, the quartic of the Higgs is small, and is especially small when I run it at the high scale. Now, you know, when something is small or not small, it depends on your normalization, so there is an ambiguity. But if something is 0, it is 0. And it doesn't depend on your normalization. So there is this feature, and you see that this is also very, very flat. The beta function nearly cancels, while all these other couplings that enter the beta function are still large at their scale. And this is really crucial. Please.
What
What am I using? The equation that I was showing before. So it's, I mean, this is a one loop. Of course, those plots that I was showing you are done in next to leading order, so there are higher loop effects all taken into account. But essentially, the physics is embedded in the beta function running with standard model degrees of freedom. Okay? So as I was saying, this is really a peculiarity of the value of the Higgs mass that we have measured. Because if the Higgs mass had been 160, everything would have been perfectly normal. All couplings would have been roughly of order 1 at a large scale. But this is not the case. So is this a coincidence, or is there a hidden meaning? And this is, for me, it's one of the most interesting questions that the discovery of the Higgs with that value has brought up. But before I enter the speculation, I want to present another problem, because the two things may be connected. And this is the well-known problem of naturalness. If I look at my Higgs potential, and you look at the quadratic term, the one that sets the scale for the electroweak scale, therefore for typical mass scale of the masses of the particle in the standard model, you know that this is very sensitive to quantum corrections. And there are various loops that you can write, and these loops are all quadratic divergent if you do it in effective theory, and this is the expression of the quadratic divergence. As you are familiar, the quadratic divergence should be proportional to the supertrace of the theory, and you may recognize that some of the coefficients are not exactly the supertrace, and the reason is because, yes, this is a supertrace, but the supertrace is taken over the field-dependent masses. So when you're expressed in terms of physical masses, you get a different coefficient for the top. But anyway, this is a detail. But this is just a usual thing, and now you can put the requirement that these corrections are not much larger than the physical Higgs mass itself. This is not a logical necessity, but it's what naturalness is based upon, and we'll discuss it why. Now, if you require that these corrections are not larger than, say, delta times the Higgs mass, you find that the maximum scale on which you could have these corrections is of about 1 TeV, or something less than that. And this is the famous argument of why the LHC should discover new physics. Recently, there's been a lot of discussion about this principle, given that there's been no discovery. And some people even criticize in a sense, saying, "Oh, this is an idle theoretical issue that was not well posed." And my claim is that instead that I think that naturalness is not a dumb question to ask. It is not an idle theoretical concept, but it has a meaning. Of course, this does not mean that nature should follow it, but let me explain why this was. It really touches a crucial hypothesis on our theories. Naturalness is a concept that is fully linked to the use of effective field theory. And effective field theory is the tool that we use to implement a very intuitive notion, the notion of separation of scales. In simple words, separation of scales means that we don't need to know the motion of every single atom inside the moon to compute its orbit. We don't need to know the dynamics of quarks to describe atomic physics. So we can build stacks of effective theories, and one on top of each other, sort of like a matryoshka, like Russian dolls, and each one is able to describe correctly physics within a certain energy domain. And then it's connected to the other in the sense that some parameters are computable in the one at the deeper level. And has been, I think, one of the most remarkable results of modern physics to show that, indeed, nature, so far, what we've seen, follows this structure, and also that at each layer we find more fundamental physical laws. So this is what brings us towards unification. We think that, that going to a next level means finding something more fundamental, simply because we've seen this pattern in nature so far. So this is not a philosophical approach. This is just an empirical fact that nature follows this order. Does not mean that we'll continue to do it, but so far this was what we've observed. Now, there are many examples that I can go back in history, the history of science, and look at them and interpret them in terms of naturalness. Let me make a few just to give you the concept. So consider a classical theory of an electron. So I'm taking a ball, which is electrically charged. There is electrostatic energy associated with the fact that this ball is charged, and this is going to be alpha divided by r. It goes like 1 over r, and if I require that the electric energy in this ball is less than the intrinsic energy of the electron, which is me mass of the electron c squared, then I'm getting a bound on the size of this object, of the radius. So since we are doing high energy physics, instead of radius, let me talk about the inverse, talk about energy. And I'm finding from this equation that the maximum energy is something like 70 MeV. Okay? So this is bigger than an atomic nucleus. So it means that I could not squeeze my electron smaller than an atom, because if I do this, the electrostatic energy grows so much that it becomes much larger than mc squared. So there is a problem of naturalness. In a modern sense, you could already have understood at that time that there is a problem of naturalness in a classical theory of the electron. And actually, you can even do better, because if you think, okay, this electron has spin. So if I'm taking a spinning ball, a classical spinning ball, there is a magnetic energy associated with the rotation. This magnetic energy goes like 1 over r cubed, with the coefficient which is the magnetic moment of this spinning ball. The electron, again, if I require that this energy is less than mc squared, I'm getting a bound on the radius which is even stronger, 3 MeV. And actually it's curious that this example was given by Fermi and Rasetti in a paper soon after the proposal of spin. They used this argument for saying there must be something wrong in spin, because, of course, they were thinking classically of the electron. If the electron is really a spinning ball, then its energy should be much larger than the intrinsic energy of the electron. Now, we can reinterpret this in a modern way by saying, well, there's a problem of naturalness. Indeed, by the way, Oppenheimer showed that this problem it also exists in quantum mechanics, because in quantum mechanics still the self-energy grows like a power of the cutoff. Well, indeed, there is something going on before the cutoff, and this is the Dirac theory. There is a positron. And if you include in the correction not just like Oppenheimer was doing, but the quantum correction of the electron, but you also include the one of the positron, then the power growth is cancelled, and the self-energy grows like only like alpha me times the logarithm of me over r, and not like a power. So in a sense, what I want to say is that people could have guessed that there was something wrong in quantum mechanics and you needed a new state, you needed a positron, even before Dirac. Of course, this is not how history happened. You can make other examples. Take, for instance, the theory of pions. And then you can compute the electromagnetic energy of the charged pion and require that this has to be smaller than the mass difference between the charge and the neutral pion. You get a bound, 850 MeV. Well, sure enough, nature had modified the theory before this natural cutoff, and indeed, there is a rho meson that changes these quantum corrections before this maximum cutoff, because the rho meson has a mass of 770 MeV. Those are all examples which are not historical in the sense that people were not thinking this way, but there's one example which is even historical, which is the G mechanism, where people really thought roughly in this way, in the sense that if you take a three-quark theory and you compute the loop contribution that generates the mass difference between K long and K short, you find that the cutoff of the theory has to be 2GeV. Therefore, you could conclude there must be something else other than three quarks. And sure enough, there is a fourth quark, there is a charm, at a mass which is below. Okay, it worked. So is it going to work for the Higgs mass? Same problem. Same problem. Now I have quantum correction to the Higgs mass, and if I require that this quantum correction are not larger than the intrinsic energy of the Higgs boson itself, then I'm getting a bound on the scale of this quantum correction. And as I showed you before, this bound is below TeV. So where is the new physics? Well, we don't know. It could be around the corner. It could be that we've been unlucky and it's going to be discovered as soon as the LHC turns on with higher energy. I think really it's true that the final verdict has not been pronounced yet. We'll have to see. Could be that there's a mild tuning. Mild tuning, I'm a little bit skeptical about this because you see, in all the examples that I was showing, I mean, nature is not stingy. When there is a naturalness problem, it just solves it before. It doesn't wait to just tune it a little bit. And it could be the case, but it just goes against the logic of the game to me. Of course, the other possibility is that our approach was wrong, that the idea of an effective theory approach on which this argument of naturalness are based fails. So everything that we've seen so far ends at the electroweak scale, and then there are new paradigms that come in, and therefore just the breaking of naturalness will give a hint of a failure of an effective theory approach. Now, you may even argue that we already seen some failure of effective field theory. One obvious example is dark energy. Dark energy, I can use exactly the same argument for the cosmological constant as I've done for the Higgs mass, and I'm finding that there is a naturalness cutoff on the fact that power divergences to the cosmological constant are not larger than what has been observed, and at a cutoff at about a milli eV. And so far, we've not seen new physics at those scales. But maybe there are other sort of subtle indications that there is something wrong with our approach. I mean, all the development in holography, in gauge gravity duality, ADS-CFT correspondence, show that some of the theories are much richer than what a single Lagrangian can capture. So the best we can do is usually to describe the same physical content with two different Lagrangians, two dual versions. But maybe this is an indication that just the theoretical tool, the language that we are using, is failing, and maybe therefore the effective field theory approach of a Lagrangian is not able to catch all the underlying physics. Maybe there are examples of theories in which there is an infrared ultraviolet connection which obviously goes against the separation of scale, which is intrinsic of effective field theories. As a joke, more than a real thing, for sure I can show you just some numerical games. If I take the largest scale in the universe, Hubble scale, and then I take the smallest scale that I can imagine, the Planck length, and I start taking geometric averages of those two, I'm getting the simple geometric average gives exactly the value which is of the size of the cosmological constant. And then if I take it now one more geometric average, I'm getting the weak scale. Obviously, I mean, I don't have any theory to defend this kind of formula, but what I want to say is that if there's anything behind this formula, this will never be it'll never be caught by an effective theory. Of course, the other possibility that people are envisaging is a possibility of the multiverse that you are familiar. In that context, then anthropic arguments may play a role in selecting the kind of universe we live in, meaning that some of these questions that we are asking are just not good questions. In a sense that they don't have any more significance than the shape of the continents or the emergence of a CERN animal species in Darwinian evolution. It's just out of the million possibility, we're just facing with the one. Of course, this to some physicists sounds like a crazy idea, science fiction, and so on. But after all, the multiverse gives the most convincing or almost the only existing explanation of the cosmological constant. So who knows, maybe there is some truth here even in electroweak physics. What I want to emphasize is that really physics is now confronting a crossroad. And this problem of naturalness versus unnaturalness is not just a problem of the electroweak scale, but it is a crucial problem that will really define the future of our field. And when I say our field, I mean not only the phenomenology, but it goes all the way to string theory, and it goes also to the experimental strategy, because of course this is crucial also for how we can address nature experimentally in the future. Now, even the problem of naturalness can be viewed as a problem of criticality. Let me explain why. I said that the Higgs potential has this form. And so if I look at the phase diagram of the Standard Model as a function of this bilinear term, I find that I have two phases. When this mu square is positive, I have unbroken electroweak symmetry. When it is negative, I have broken symmetry. I could be anywhere in principle in this phase diagram. Well, actually, the naturalness problem tells me that that's not true, that there is a pressure to be either far to the right or far to the left, just because quantum correction tend to push you away from the origin. Then there is observational fact that we just live at the border between these two phases. There's no scale. There's no scale. I mean, this is okay. So this here is 250 GeV squared, okay? Because this is a Standard Model. How far does the naturalness push you? It depends on your cutoff. So you can view this as a Planck scale if you want, and this Planck scale square, and this minus Planck scale square. So what I want to emphasize is that with respect to this scale, the 250 GeV square is a very small number. Of course, if you bring down the cutoff, then you know, but this is the whole issue about naturalness, right? So now you can rephrase the problem of the Higgs naturalness is, why are we so close to the critical line? And you see, this is exactly the same way I was phrasing the problem of the quartic coupling. So both can be viewed as a problem of criticality. We don't know. Maybe it's symmetry that solves the problem, because after all, symmetry has a potential to do it. Because take supersymmetry. Supersymmetry tells you that this mass square parameter must be exactly 0 in the supersymmetric limit, which is what you want, because you want to be very close to 0. So if you break supersymmetry only a little, you've done. Actually, even the fact that the quartic coupling is 0 could be explained by supersymmetry, what's called tangent beta equal to 1 limit. Tomorrow, maybe we'll talk about supersymmetry and we'll see. Or you can say maybe there's a Goldstone symmetry. After all, the Goldstone symmetry tells you that the potential is 0. So it would explain why lambda is 0 at some very large scale, and then who knows what happens. Or the alternative possibility is that this criticality is due to a statistical explanation. We don't know what is happening. I mean, there are many statistical systems which approach criticality. Think of self-organized criticality. Think of, I could give you also lots of physical examples that maybe I'll skip. In all these systems, the critical point is not reached because of symmetry, but simply the dynamics is just that there are conflicting forces that push you towards the critical value. So could that be that there's something like that also for the Higgs? Well, if that is the case, necessarily you will need to have an underlying system which is a statistical system. And when you talk about it, of course, the multiverse is the first thing that comes to mind. But you see that in this case, you get a different interpretation of the multiverse, because usually, like in the case of the cosmological constant, people think, okay, there's a pressure. I mean, the vast majority of the universe have a large cosmological constant, but we just happen to live in this one because anything larger than the observed value would go against the anthropic principle. But if criticality is true, maybe there's a different interpretation, that our universe is not a special element in the multiverse, where there is a peculiarity of the parameters because of allowing for life, but rather a universe is just one of the most common products of the multiverse, and it's near an attractor critical point. So statistics, in that case, and not an anthropic argument, would play a role, but still inside the multiverse. So the other possibility, of course, is that naturalness is cured by symmetry. Because I can interpret the problem of naturalness as a difficulty to keep fundamental scalars much lighter than the scale of validity of the theory. And this is the usual approach that people follow. Let me give you an example. In the case of QED, the electron, we know that the mass of the electron is very small with respect to other scale in physics, but that does not cause a problem. Why? Because if I look at the mass renormalization in QED, the mass renormalization has to be proportional to the electron mass, just by dimensional analysis, times a logarithm. This is exactly the logarithm that we were seeing before, right, when I was discussing the self-energy of the electron. So the crucial point is that quantum corrections to the electron mass are proportional to the electron mass itself, so that renormalization is only multiplicative. And so there are, by dimensional analysis, only log divergent quantum corrections. And this is why the electron mass can be naturally small, naturally in the sense of really the TeV principle. And the reason is because M is protected by a symmetry. And in this case, it's chiral symmetry that plays a game because, as you know, this theory has a global invariance a global invariance in which you transform the left and the right electron differently. Now, the mass is, once you include the mass, this symmetry is not respected anymore. And since m is the symmetry breaking coefficient, any correction to the electron mass has to be proportional to the symmetry breaking parameter, which is m itself. And that's why it follows. And the same argument can be applied, for instance, to gauge bosons. We've seen it already. Like, the gauge symmetry has a nonlinear transformation, therefore forbids the vector boson mass, or the Goldstone symmetry, which is a shift symmetry and forgets a mass. So the question is, what is the symmetry that protects this mass term? And if we just look at the standard model, we do not identify any. In the sense that setting this parameter to 0 does not increase the symmetry of the problem. There is a physical interpretation to this, and let me, for instance, take an electron, right? A massless spin 1/2, a massless electron has only one helicity. But as soon as I go to a massive particle, I necessarily must have two helicity. And the reason is pretty obvious, because if I take, for instance, one electron that has the spin in this direction with respect to its motion, the spin in this direction with respect to its motion, then I can always take a boost, go in another system. In the other system, the spin will always be the same, because I'm not changing spin. But if I go faster than the electron, its momentum goes in the other direction, meaning then I'm changing helicity. So for a massive particle, there's no way that I can have a particle with only one helicity. Necessarily, I need to have two helicity. So the massive theory must have a new state. This is exactly, if you remember, I think it was the first lecture, when I discussed the problem of electroweak symmetry for the spin 1 particle, it's the same. The spin 1 particle has 3 helicities when it's massive and only 2 when it's massless. And that's the reason why quantum corrections in this case are multiplicative. So here we go. We are facing this problem, and I conclude. Okay. This is a last transparency. There are many strategies that people have, that physicists have proposed to attack this problem. And as I said in the beginning of my lectures, all of these ideas are really beautiful, and they go beyond, I think, the problem itself. Some of them are a really new conception of space-time, of our understanding of the fabric of space-time, of the forces, and so on. Now, let me just review them quickly. One possibility is to use the symmetries that I was showing that do protection and translate them to a scalar particle. So, for instance, I could take the chiral symmetry that protects a spin 1/2 particle, and then invent a symmetry, supersymmetry, that relates a spin 1/2 to a spin 0 particle, and here we go. I protected the mass of the Higgs. Another possibility would be to use the Goldstone symmetry and interpret the Higgs as a Goldstone particle. Of course, it cannot be an exact Goldstone particle, but it could be like a pseudo-Goldstone particle. And this brings to what are called composite models. The other possibility would be to use the gauge symmetry that protects mass and relate scalars to vector fields. And this can be done in theories with extra dimensions, in which the gauge field of the extra dimension, when it's projected into 4 dimensions, carries extra components, which are scalars with respect to the Lorentz group in 4 dimensions. Another possibility would be to eliminate scalars altogether, and this is the old idea of Technicolor. Well, this is the first victim of the LHC. Now we've discovered a scalar, so Technicolor is dead. Of course, people think that maybe out of the tomb it could come out because the Higgs may not be a Higgs, may be an impostor, may be, for instance, like a dilaton, and then we discover there was no Higgs. We'll see. Other possibilities is that there are, out of this strongly interacting sector of Technicolor, there are some light particles. Like the pions are much lighter than the typical QCD scale. It could be there's something like that. But that brings back to the idea of pseudo-Goldstone bosons, which now is called composite models. And another possibility would be to eliminate a hierarchy, like it's done in extra dimensions. Now, as I said in the beginning, I will not review all these possibilities, which are beautiful. But in the last lecture, I will just make some comments on the first two possibilities, because those two are the ones that are most relevant for the Higgs problem, and here we are discussing just the Higgs. Thank you.
Thank you, Gian. So at 5 o'clock today, we will have a discussion session with Gian. We still have time for a few questions.
Sure, people want to go for lunch more than...
People are hungry, but I have one question. In the first half of your talk, when you talked about the stability issues, you were saying that top quark should be, the mass should be known with higher accuracy. Right now, if I'm not wrong, it's something like 1.5 GeV, 1%.
Right.
Pretty good, I would say.
Yeah.
Is there any hope of improvement?
Well, I mean, the LHC right now has reached a precision which is not much worse than the Tevatron, and which is also, by the way, another remarkable result of the LHC. And soon it will really compete and get and be better. However, we cannot aim at a precision which is much better than the GeV at most. Really, it would be. And here, it would be interesting to go beyond. The only possibility would be in a linear collider. In a linear collider, you are in an environment in which you can do better, and there you could make a much more precise measurement of the top mass. At that level, however, there are even theoretical issues of what is the top mass. I mean, when they measure something, how do you relate it to the real pole mass? And there are subtle issues because, of course, you know, the top is not a stable particle, and it's something that hadronizes. So going from the top mass of what experimentalists mean by top mass and what we mean by top mass, there are subtle theoretical issues. So this is something that will be really for the future if and when a linear collider will be built.
Okay, let's